Hi everyone, and welcome to today's webinar about modeling the hydrogen electrolyzer system in Flownex. Globally, engineers are striving to find practical green energy sources to reduce CO2 emissions, and hydrogen is a promising solution. The two most common ways of producing hydrogen are steam reforming and electrolysis. Electrolysis is much more environmentally friendly in producing hydrogen. Such electrolysis plants are made up of many complex components and are expensive to build. Time and effort should be spent during the design phase to ensure that the plants will function safely and optimally under varying operating conditions. Using simulation software for these plant designs has become crucial to save time and money. Is it possible to use Flownex to model an electrolysis plant and investigate the plant's performance? Stick around, we are going to find out. To introduce myself, I am Barend Meyering, one of the simulation design engineers at Flownex, and I will be presenting this webinar today. Before I continue, I would like to explain the webinar interface and how to ask questions. You will see a question tab on your right hand side, and please feel free to type in a question at any point in the webinar, and we will answer all your questions at the end. For today's agenda, we will be looking at electrolyzers and how it works, different types of electrolyzers and system components, what Flownex is and how it can be used to aid engineers during the design process of electrolysis plants. Water electrolysis has been around since the late 1700s and has since become a well-established technology for miscellaneous applications and mostly for the production of hydrogen. It is estimated that around 1900 more than 400 industrial alkaline electrolyzers were in operation. In the late 1960s, the development began for proton exchange membrane electrolysis and for high temperature electrolysis of solid oxide cells. The interest in electrolysis has grown significantly in the past few years due to the climate crisis and global interest in creating a net zero emission future. Electrolyzers makes use of electrolysis to produce hydrogen and oxygen. Electrolysis is the process of breaking water into hydrogen and oxygen through electricity. The resultant chemical reaction during electrolysis is that 2 moles of water are converted into 2 moles of hydrogen and 1 mole of oxygen. The production of hydrogen is classified into 3 main categories: grey, blue and green. Grey hydrogen is when carbon dioxide is released during production. Blue hydrogen is when carbon dioxide is captured during the production process, and green hydrogen is when no carbon dioxide is released. Green hydrogen production is achieved by using renewable energy as an electrical source for electrolysis. Using electricity generated through a nuclear plant as an energy source to produce hydrogen is also referred to as pink hydrogen. The 3 different types of electrolyzers are proton exchange membrane, or PEM, alkaline and solid oxide electrolyzers. These electrolyzers differ in operating conditions and type of electrolytes, which we will look at next. The table compares the different electrolyzers in terms of operating temperature, operating pressure, cathode and anode gas, membrane and electrolyte. From the table, you can see that the operating temperatures for the PEM are the lowest. The alkaline electrolyzer has a bit higher range, and the solid oxide electrolyzer has a very high operating temperature. The operating pressures for the PEM and alkaline electrolyzers are up to 30 bar, whereas the operating pressure for a solid oxide electrolyzer is up to 10 bar. The PEM uses a polymer electrolyte membrane, the alkaline uses a potassium hydroxide electrolyte, and the solid oxide electrolyzer uses a solid ceramic material for an electrolyte. There is a lot of scientific material describing electrolysis and the different types of electrolyzers, if you'd like to read up on it after the webinar. Alkaline electrolyzers have come a long way and are currently the most commercially used to produce hydrogen. We will use a simple alkaline electrolyzer to investigate a system's power consumption and controllability. To do that, we need to build an alkaline electrolysis system in Flownex which can help us analyze the parameters. The The process flow diagram on this slide was used to model an alkaline electrolysis plant in Flonex. I will briefly discuss the process flow and the different components. Water is added to the hydrogen separator and the alkali tank. Potassium hydroxide is also added to the same alkali tank. A circulation pump is used to circulate the solution through the electrolyzer and separators. Hydrogen gas and oxygen gas are produced in the electrolyzer, are separated in each of the respective separators, and tapped off for process-related use. Cooling water is also used to cool down the produced gases. A Lie cooler situated between the hydrogen separator and the circulation pump are used to cool down the solution to ensure that the alkaline electrolyzer is operated at the safe temperature. We can now identify what is required to simulate an alkaline electrolysis plant. We need to model a mixture of potassium hydroxide and water for the alkaline solution that is circulated through the system. We need a gas and fluid mixture model to track the flows and thermodynamic properties of the gases produced in the alkaline solution. We need a way to describe the electrolysis reaction in the electrolyzer stack. Critical parameters that needs to be calculated are the amount of energy required for the reaction process, the amount of reactants required, the amount of products that will be formed, and the amount of heat that will be generated. The amount of work required to pump the alkaline solution through the system and to pump the cooling water to be used to cool down the produced gases needs to be determined as well. We need control models to investigate start-up and operational conditions. Focus areas will be regulating the potassium hydroxide concentration of the alkaline solution to enhance the electrolysis process. Water will be consumed and converted into hydrogen and oxygen, which will influence the concentration of the solution. The cooling of the alkaline solution and produced gases needs to be investigated as well. The temperature of the alkaline solution must be regulated due to heat generated from the electrolysis process to ensure safe operation. The amount of heat required to cool down the produced gases to aid in storage must be calculated as well. We need pressure drop models to model flow and flow control such as piping and valves. How does Flonex fit in with the solution? And is Flonex capable of modeling the system that has been described? Let me take a moment to discuss Flonex and its capabilities. Flonex is an engineering tool that can be used by engineers in the design and analysis process of thermal fluid systems. It solves the fundamental physics for flow and heat transfer components of large thermal fluid systems. Flonex uses a one-dimensional approach in solving systems. Flonex does this by solving the conservation equations of mass, momentum and energy on component level. All components can be solved fundamentally in true steady state as well as transient with either fixed or adaptive time steps. Flonex houses a large library of standard components used in industry, advanced fluid models, control library and integration with third-party software such as ANSYS, MATLAB and Excel. Ensuring for the best standards of quality compliance, Flonex is developed within an NK-A1 and ISO 9001 environment. Flonex also has a user-friendly interface with a help manual that can be quickly accessed and contains detailed explanations of each component and provides guidance on how to specify inputs and interpret results from the simulation. Having a look at the typical requirements of modeling an alkaline electrolyzer and what Flonex can offer. Flonex has a vast library consisting of liquids, gases, two-phase fluids, and the added capability of creating gas mixtures or liquid and gas mixtures. The NIST importer can be used to import custom fluids created in NIST or to expand the temperature and pressure ranges of existing fluids in Flonex. The chemical reaction in the electrolyzer stack can be modeled by using a built-in CIA chemical component. Custom reactions can be implemented in Flonex using scripting with C# based programs, Ease and Python. Flonex can be integrated with external programs such as Cantera or MATLAB to describe the stack. The electrolyzer stack can also be implemented in Flownex as a reduced order model or by co-simulation using the FMI capability of Flownex. Flownex provides the user with simplified pump and compressor models to design these components for different flow rates and pressurizers. Complex models are included where you can add the pump charge or compressor maps obtained from suppliers. Flownex has a built-in control library with analog and digital controllers to aid the user in investigating controller performance and stability. A library of common heat exchanger models is included in Flownex, such as Shannon tube, Finnan tube, plate heat exchangers, etc. Flownex also allows the user to add custom heat transfer correlations. Flownex has a vast library of typical pressure drop models such as pipes, valves, etc. These include simple to complex models depending on availability of specific input data. Let's go over to Flownex to look at a simple alkaline electrolyzer model I've built and see how we can use Flownex's functionalities to analyze the power consumption and controllability of the system. Here is the alkaline electrolyzer model I've built in Flownex. The different components are the makeup water supply tank, the valve that controls the supply of water to the system, the potassium hydroxide supply tank, the valve that controls the supply of potassium hydroxide to the system. We have our circulating pump, we have our lye cooler, we have our separate separators, we have our electrolyzer, we have our hydrogen product stream, our produced oxygen product stream, and also the cooling thereof with Finnan tube heat exchangers. We have also a PID controller that controls the supply of water to the system. I've created two graphs that tracks the overall power consumption and the conditions of the electrolyzer parameters within the system. These parameters are the temperature and concentration in the electrolyzer. The overall power consumption is calculated by adding the power consumption of the circulating pump, the solution cooler, the electrolyzer, and the cooling pumps. The scripting functionality in Flownex was used to describe the reaction and heat generated in the electrolyzer. The script uses the amount of hydrogen to be produced as an input parameter to calculate how much oxygen will be produced, how much water will be consumed, how much heat will be generated, and how much power is required to drive this process. A custom fluid was also created for this model. I made use of the gas and liquid mixture functionality to create a mixture between the 50% concentrated potassium hydroxide, water, hydrogen, and oxygen. A transient simulation to model the startup of the electrolyzer was set up in Flownex with actions. Firstly, the potassium hydroxide solution will be circulated through the system. The water valve will open and the potassium hydroxide valve will close as soon as a set level has been obtained in the separators. The water valve will remain open until the desired concentration of potassium hydroxide have been achieved in the electrolyzer. When the system has stabilized, the electrolyzer will switch on and the cooling pumps will switch on shortly thereafter to cool down the produced gases. The alkaline solution cooler will switch on as soon as the solution temperature goes to high. This is to ensure that the electrolyzer is operated at safe temperatures. So let's run the transient and see how the system responds during startup. Firstly, I'm going to load my snap, going to solve steady state and run transient. While the transient simulation is running, we can keep track of the system power consumption and see how the power increases as different parts of the electrolysis plant are switched on. As you can see, the power increased with the alkaline pump switching on. I've also added some indicators to show whether the components are on and off, with green being on and off for the off components. We can also monitor the conditions of the electrolyzer tank to determine if the electrolyzer is operated at safe and optimal conditions. As you can see, for the electrolyzer, we are stable at the temperature of 50 degrees Celsius, and we are approaching a desired concentration of 30%. Now we will wait for the system to stabilize, and thereafter the electrolyzer will switch on. We can keep track of the real-time simulation at the bottom right, and we can see we are now at 14 minutes. After 15 minutes, the electrolyzer has switched on, and as you can see, there's a steep increase in power consumption as well as heat generated due to the electrolysis process in the electrolyzer. The two cooling pumps has also switched on to aid in the cooling of the two produced gases. Let's quickly have a look at the PID controller. Here you can see the input for the PID controller. You have your proportional gain, your integral time, derivative time, the output high limit, output low limit. Due to the fact that we are controlling the valve, we have a limit of opening of 1 or 0. The process value we are looking at is the concentration in the electrolyzer tank, and the set point we use are 1225. This is to achieve an optimal potassium hydroxide concentration of 30%. As mentioned before, we used the script functionality of Flownex to describe the electrolyzer stack. The chemical equations are written as simple C# code and can be easily changed for the different types of electrolyzers and operation. The electrolyzer stack can also be described by coupling Flownex with external programs such as MATLAB or ANSYS. As you can see, we are now at a real-time simulation time of 32 minutes, and we can see that the system are starting to stabilize in terms of power consumption as well as the temperature within the electrolyzer tank. We can also note that the solution cooler has switched on to maintain the safe operating temperature within the electrolyzer at about 70 degrees Celsius. And the overall power consumption are currently at 6.3 kilowatts. At any point during this simulation, if you want to track any other parameters within the system, you can just click on the components and view the results at that point. You can have a look at the low pressure storage as well as our fin and tube heat exchangers, and that is our startup transient simulation of an alkaline electrolyzer in Flownex. Such models can be used to test additional scenarios such as unwanted valve closures, pump trips, electrolyzer trips, compressor trips, inadequate power supply, to see how the rest of the system will respond. That is the end of the demonstration in Flownex. I would like to take time and summarize the webinar. Flownex is a tool that engineers can use to design, analyze, optimize, and evaluate complex thermal fluid systems. This includes thermal management, power consumption analysis, failure mode studies, control stability investigation, feasibility studies, performance and efficiency studies, etc. Where power consumption and control stability are important parameters to investigate during the design phase of electrolysis plants, Flownex provides a way of tracking these during real-time simulations. Flownex can model complex fluids and mixtures with the ability to import custom fluids. Custom components can be created in Flownex to model the electrolyzer stack, or Flownex can be coupled with external programs. Flownex has a large library that ranges from basic to complex models. Various pressure drop models such as pipes, valves, etc. Heat transfer models with common heat exchangers, a control library with analog and digital controllers, and turbo machinery components to model pumps and compressors. With engineers worldwide striving for a better and greener future, using a system simulation software such as Flownex can help to fast-track the design process, saving time and money. If you are interested in Flownex and want to try it, please visit the Flownex website and request a demo under the Contact Us section. Alternatively, you can reach out to us by sending an email to inquire@flownex.com. If you are an existing client and would like a copy of this network, please send an email to support@flownex.com. And this brings me to the end of this exciting webinar. Thank you for joining, and I hope that this has given you a better overview of what Flownex is capable of in the hydrogen industry.